So now we turn to another problem where we're trying to find the derivative. Again, using our limit definition, we have f of x equals the square root of x. And so we begin using our limit definition. It'll be limit as h goes to 0 of f of x plus h. So we put x plus h into the square root. So we get square root of x plus h minus square root of x all over h. And our goal again in this limit is we want to get rid of that zero factor. It has to go away for us to be able to evaluate this. So one thought might be, well, let's square it, but there's no both sides to it. And squaring that quantity on top there actually won't make it go away. Even if we did square it, and then later on maybe come back and take the square root of our answer, squaring it's just not going to make that go away anyway. So that's still actually a problem. The key here is something that you might recall doing with complex numbers when you were dividing them. Maybe you even remember doing it with square roots when you'd have something like 5 over, square root of 2 plus 1. You had to do what was called rationalizing the denominator. And so what we're going to actually do here is rationalize the numerator. And the key idea is this result, is recalling that if you multiply something in the form a minus b times a plus b, it becomes a difference with squares. So when we have a subtraction or actually an addition problem, it would work with an addition problem too, and we wanted to make that get rid of the squares, we could multiply it to make it a difference of squares. And that's what we're going to do here. Is we need to make that into a difference of squares. That way we'll have the first thing squared minus the second thing squared. And when you square a square root directly, it does go away. And so here we're going to need to multiply by square root of x plus h plus the square root of x. Right, if you think of square root of x plus h as being your a and square root of x as being your b, then we're multiplying by a plus b. But since this is a fraction, we can't change it by just pulling that out of nowhere. We also do that in the bottom. And now we go ahead and we simplify. Okay, so when we multiply through in the top, square root of x plus h times square root of x plus h, square roots just go away. So we just get x plus h. And again, it's a difference of squares, so all the middle terms are gone. And then we have square root of x times square root of x, which would just be x. And then in the bottom, we'll have h times square root of x plus h plus square root of x. And now everything kind of simplifies pretty nicely. The x's go away. So that the only thing in this problem that's left in the numerator now is just h. The only thing left in the numerator now is just h. And so that h can cancel with the h in the bottom, getting rid of our zero factor and leaving us now with the limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x, freeing us up now to evaluate it by allowing h just to become 0. And doing so would give us 1 over square root of x plus square root of x. But a better name for square root of x plus square root of x is to call it 2 square roots of x. 2 square roots of x. And we're content to leave the answer like that. Yeah, you might be thinking, well, don't I have to rationalize? I guess if someone really wanted to be technical about it, they could say, yeah, you do, but we generally don't at this point in calculus. We generally don't bother with the idea of rationalizing a function. So we get the answer 1 over 2 square roots of x.